Welcome back to the lecture series on Foundations of Deep Learning, Concepts and Applications. In our last session, we have seen the architecture, implementation and the performance of AlexNet. In today's session, we will look into two more standard CNN models, the VGGNet and the GoogleNet. So, the contents of today's session are Introduction to VGGNet, variants of VGGNet, VGG16 and 19, detailed architecture of VGG family, impact and limitations of VGGNet. Then we come to GoogleNet, its Inception module and GoogleNet architecture. So, what is the motivation and historical context for VGGNet? So, we will see what happened after AlexNet. AlexNet, we know that it has made a brilliant performance in the 2012 ImageNet dataset large scale visual recognition challenge. And after AlexNet, what happened is researchers started thinking or hypothesized that increasing the depth, that is stacking more convolution layers, would improve the hierarchical feature representation, allowing the network to capture more complex patterns. However, the computational resources and training stability were still a challenge. The VGG models were introduced by Karen Simonian and Andrew Zisserman from Oxford University in their 2014 paper titled Very Deep Convolution Networks for Large-Scale Image Recognition. The primary objective was to investigate the effect of increasing the depth of CNNs on large-scale image recognition tasks. So, this group of scientists, Karen Simonian and Andrew Zisserman, they tried to investigate in a very systematic way what is the impact of increasing the depth of CNNs on large-scale image recognition tasks. This is the reference for this paper. Now we will see what this VGG architecture consists of and what are the innovations of VGG architecture over AlexNet. In AlexNet, we have seen there were large filters like 11 cross 11, but here in VGG, the main idea is to use, instead of using very large filters, they used small filters, 3 cross 3 filters, but they are stacked in layers. This reduced the number of parameters compared to large filters, and it is a simple architecture. So, the receptive field can be kept constant by or kept same by using small filters, layered on stack. So, that is the main idea of VGG architecture. The VGG family includes various configurations with different depths denoted by the letter VGG followed by the number of weight layers. So, this includes VGG11, VGG13, VGG16 and VGG19. We will look into VGG16 and 19 in detail because they are the ones which are very much used. So, VGG16 have 13 convolution layers, 3 fully connected layers and 138 million parameters. Whereas VGG19, it has 16 convolution layers, 3 fully connected layers and 144 million parameters. Now, we will have a look into the detailed architecture of VGG16. It consists of several blocks. The first block is having convolution, 2 layers of convolution. Each layer of convolution is having 3 cross 3 size filters, 64 in number. So, 64 filters 3 cross 3, another convolution layer 64 filters 3 cross 3 and then the max pooling layer of 2 cross 2. The output size is 112 cross 112 into 64. This is coming from the input image size, which is 224 by 224. We will see it in the next slide. Block 2 consists of once again 2 layers of convolution, each having 128 filters, but the filter size is kept constant and then there is a max pool layer of 2 cross 2. The output size here is 56 cross 56 into 128 and 56 cross 56 came because there is a max pooling layer which reduced the dimension from 112 to 56. Block 3, once again there are 3 convolution instead of 2. In the first 2 we have seen 2 convolution layers are there. Here in block 3 we have 3 convolution layers. Each of these layers have 256 filters of size 3 cross 3 and max pooling of 2 cross 2. Output size is 28 cross 28 into 256. Block 4 once again has 3 layers of convolution and each having 512 filters, and finally one max pool layer of 2 cross 2. So, every layer we see the number of filters are increasing till this one increasing, and the spatial dimension is decreasing because of the max pooling layer. Block 5 almost same as block 4, 512 filters, 3 cross 3, and there are 3 such layers of convolution and a max pool. So, the output size is 7 cross 7 into 512. Then we have the fully connected layer which is having 4096 units with a ReLU activation, fully connected layer 2 which is once again the same thing, 4096 units with ReLU activation, and then we have the fully connected layer 3 which is having 1000 units with softmax for ImageNet classes, because ImageNet have 1000 classes. Now, we will have a look, a visual representation of the VGG16 architecture. So, if you have an image, input image 224 cross 224 cross 3, it is a colored image. Then this is a convolution layer for plus ReLU, and so like this, each of these convolution layers, there are 64 filters, and the size will be 224 into 224 into 64. Then we have this max pooling layer which reduces the spatial dimensions to 112 cross 112, and 64 comes from the number of filters that were there in the previous layer. So, this consists of my block 1. Similarly, there are another two convolution layers, each of them having 128 filters. So, the size is 112 into 112 into 128, and there is the green colored one is a max pooling layer which reduces the spatial dimension from 112 to 56 cross 56, and 128 comes from the number of filters. So, this is my block 2. Then block 3, in block 3 there are once again 3 convolution layers, each having 512 filters. The spatial size is 56 cross 56, and finally there is a max pooling layer as well, and which reduces the spatial dimension from 56 to 28 cross 28. Then we have the fourth block, block 4, which is once again having 3 convolution layer, 1 max pooling layer, and the dimensions are 14 cross 14 into 512. And then we have block 5, which is reducing the size to 7 cross 7 because of the max pooling layer and convolution layers. There are 3 convolution layers, each having 512 filters. So, the size is 7 cross 7 into 512. Then we have this fully connected layers which are having 4096 nodes, and this takes input, flattened input 1 cross 1 input 1 cross 1 into 4096, and then we have the softmax layer for the classification task, and there are 1000 nodes in that softmax layer. So, this is the architecture of VGG16. Now, we will see how VGG19 is different from VGG16. So, if we see here, the input image size is 224 cross 224 into 3, and same as we have seen in VGG16 architecture. Then block 1 is exactly same as that we have used in VGG16, having 2 convolution layers, each having 64 filters of 3 cross 3, max pooling layer of 2 cross 2. Then block 2 also same convolution, 2 convolution layers of 128 filters of 3 cross 3 size and max pooling layer 2 cross 2. And then block 3 is the place where we have a change. So, here instead of 3 convolution layers which was there in AlexNet, in VGG16, here we have 4 convolution layers, each of them having 256 filters and then a max pool layer. Block 4 also there is a change. There are 3 plus 1, 4 convolution layers and max pool of 2 cross 2. Sorry, in block 3 also there are 4 convolution layers, max pool 2 cross 2, and in block 4 also 4 convolution layers of max and then a max pool of 2 cross 2. Block 5 also there are 4 convolution layers. Each of these convolution layers have 512 filters and the spatial size of these filters is 3 cross 3. So, everywhere across VGG architectures the kernel size is kept constant, which is 3 cross 3. Only the number of filters keep changing with every block. 1, 2 and 3 blocks we have seen. Number 4 also the number of filters have changed in block 4 also, but the spatial dimension of the kernel size is same. And then we have the same fully connected layer here having 4096 units with ReLU activation, fully connected layer 2 also same, and fully connected layer 3 also having fully connected layer 3 is having 1000 units for the softmax activation function for ImageNet classes. Okay. So, the only difference between VGG16 and 19 is in block 3, block 4 and block 5, where instead of 3 convolution layers, here there are 4 convolution layers. So, totally there are 3 extra convolution layers which makes VGG16 to VGG19. So, we will have a look into the architecture in a visual way. So, this is my input image, this is my convolution layers and max pooling layer, this is the block 1 as we have seen in VGG16 architecture. Then we have the block 2 which is also having 2 convolution layers and a max pool layer. Then from block 3 onwards we have 4 convolution layers and 1 max pool. Then block 4 also is having 4 convolution layers and a max pool layer. Block 5 also is having 4 convolution layer and 1 max pool layer, followed by the fully connected with ReLU activation function and finally the softmax activation function. But what scientists have observed is VGG19 is deeper than VGG16, but the accuracy gain over VGG16 is very less. It is around 0.2% in ImageNet dataset. So, they did not go more in the depth because the accuracy was accuracy gain was not that promising. So, what is the impact and what are the limitations of this VGGNet? So, VGG16 secured the first runner-up in the ImageNet large-scale visual recognition competition in 2014 in the classification task with a top 5 classification error of 7.32%. So, this is much better than AlexNet also, and it is the state of the art object recognition model. But there are certain limitations of VGG16. The number of parameters were huge, around 138 million parameters, mostly once again coming from the fully connected layers, which required large storage space, and it was very slow to train. So, these were the limitations of VGG16, and once the number of parameters become very high, we need very powerful GPUs and lot of training time. So, these were the limitations of VGGNet, but still VGG16 showed a very promising result in the competition ImageNet large scale visual recognition competition in 2014. But they were the first runner up. Now, who is the winner? So, we will see who is the winner of this 2014 championship or competition. It is no one other than GoogleNet. So, we will have a look into what is this GoogleNet architecture, how it has improved its performance over VGG family, and what are the innovations in this GoogleNet. So, GoogleNet is also called as the Inception V1. The motivation is the previous CNN architectures such as AlexNet and VGGNet had a limited number of layers. So, VGG16 had 16 layers, and here this limited their ability to learn complex patterns. Architectures were not very computationally efficient. GoogleNet addressed this challenge of previous CNN architecture by introducing the conception of Inception module. It's a 22-layer deep convolution network. So, it is much deeper than VGG16. And the main innovation is in the Inception module. We will see what is the Inception module and how it helps to overcome the limitations of VGG16. Unveiled by researchers at Google in 2014, it introduced a novel approach to design deep neural network which achieved exceptional accuracy, computational efficiency. Computationally it was efficient and won the ImageNet large scale visual recognition challenge in 2014. Okay. So, we will now understand what is this Inception module. Now, in your standard CNN modules, they are made up of convolution layers plus activation layers, pooling layers, dense layers. These are the main components of a standard CNN. And in traditional CNNs, we use one kernel size per layer, like a 3x3 or a 5x5 convolution. But here, if you see an image, features in an image can vary in scale. So, edges, textures, objects can be of different sizes. So, limiting one kernel size per layer, it was increasing the number of parameters and which was taking a lot of training time. So, that is something which Inception module tried to solve using something called as the 1x1 convolution. So, the core idea of Inception module is, why not look at the image using multiple receptive fields at the same time. So, the idea is, instead of choosing one type of convolution filters like 3x3 or 5x5, Inception module applies multiple filters in parallel to the same input and then concatenates their output. So, parallelly Inception module is looking into various places using multiple filters, and finally they are concatenating the output of these filters and giving the output prediction. So, that is the core idea. The reference paper is going deeper with convolutions. So, this is the reference paper. I urge all of you to look into this one. Now, in Inception module, they have used something called as 1x1 convolution module to improve the number of decrease the number of parameters and improve the training time. So, what is this dimensionality reduction using 1x1 convolution module? We will have a look into that now. If we have a traditional 5x5 convolution operation, suppose I have an input coming to a layer which is of size 14x14 into 480, and I want a convolution operation of 5x5 to be done over this input feature map, and number of filters in my convolution step is, number of filters is 48. Then what is the output size I get is 14x14 into 48. Now, we will see how many operations are there in this traditional 5x5 convolution. Number of operations, we know number of operations can be calculated as the output images or output feature maps dimensions, H out into W width output into the channel output into the kernels or the filters width and multiplied with the filters height into number of input channels. So, multiplication of the output feature maps height, width and channel into the filters width and height into the number of channels. Okay. So, if we see this traditional 5x5 convolution operation, the number of operations involved here is 14x14 x 48. What is this 14x14 x 48 from where we are getting? So, 14x14 x 48, 14x14 is coming from the output and 48 also is from the channel number of the output into the filter width and height, which is 5 cross 5, into number of input channels, which is your 480, which results in 112.9 million parameters. 112.9 million operations. Now let us look into this same 5 cross 5 convolution using 1 cross 1 convolution as well. So we have this input feature map 14 cross 14 into 480, and then we will do a 1 cross 1 convolution. Number of filters used is say 16, and the output size is 14 cross 14 into 16, and then we go ahead and do this filter size of go ahead and do a 5 cross 5 convolution operations with 48 number of filters, and the output size here is 14 cross 14 into 48. So we are maintaining the spatial dimensions, the outputs are same, but here we have added one more convolution operation. Now this will reduce the number of operations involved. It looks a little bit counterintuitive because we have added one more operation here, but now when we go and see the actual calculations, it will we will see how the number of operations involved here are less than the traditional 5 cross 5 convolution operation. So number of operations for 1 cross 1 convolution is, it is 14 cross 14 into 16 coming from here into 1 cross 1, which is the kernel size or the filter size, into the input channel size, which is 480. So this is around 1.5 million. Now the second operation is 5 cross 5 convolution. So number of operations here is 14 cross 14 into 48 coming from the output feature maps size into 5 cross 5 into 16. 5 cross 5 comes from the filter size and 16 comes from the number of input channels. So which is around 3.8 million. So together we have 1.5 million plus 3.8 million, which is around 5.3 million. So we see there is a drastic change in the number of operations that are involved if we use 1 cross 1 convolution module before we go and apply larger size filters. Okay. Now this innovation is used in the Inception modules, which we will see here. So 1 cross 1 convolution helps in dimensionality reduction, which reduces the computation. So now we will see how the Inception module works. So we have the input layer, and this input layer goes into several operations parallelly. So these are the operations like 1 cross 1 convolution, and another one is the second one also is another 1 cross 1 convolution, then another 1 cross 1 convolution, and there is another 3 cross 3 max pooling. Now what is this 1 cross 1 convolution doing? It is reducing it is taking the raw input and reduces the dimensionality and extracting fine grained features from the image. So what is happening here is, if it is a 1 cross 1 convolution, it is looking at 1 pixel at a time across all the channels, and then it is taking out the fine grained information from the image. Okay. In the second 1 cross 1 convolution, after applying 1 cross 1 convolution, we go to the 3 cross 3 convolution. So it is after 1 cross 1 convolution is done, then it is sent for 3 cross 3 convolution. And what is happening here? 1 cross 1 convolution reduces the number of channels. 3 cross 3 convolution then captures the medium sized spatial features like the edges, corners, local textures efficiently. Similarly, the third 1 cross 1 convolution, after this one it goes to 5 cross 5 convolution, which is a bit larger sized filter, and then once again what it is doing, the 1 cross 1 convolution reduces the computation by reducing the dimensionality. 5 cross 5 convolution captures large spatial features like broader patterns and objects. Then we have this 3 cross 3 max pooling, and over that 1 cross 1 convolution, what exactly is happening? Pooling extracts contextual information by, it takes only the information that is important. 1 cross 1 convolution after pooling reduces the dimensionality. And from all these operations, this all goes to in the filter concatenation layer, and then from there we get the output. So this is how the Inception module works. Now, in the GoogleNet architecture, how is this Inception module used and where all they are used? So, we have the input image. Input image goes to convolution 1, conv 1, which is having 7 cross 7 filters with stride 2. Then it goes to max pool 1 of 3 cross 3 dimension and stride 2. Then it goes to conv 2, which is having filters of 7 cross 7 size, stride 1. Then it goes to max pool 2 of 3 cross 3 dimension and stride 2. Then it goes to Inception 3.1. There is the first Inception block, then another Inception block, then again a max pool layer of 3 cross 3 size and stride 2. Then it goes to another Inception block 1, 2, 3, 4, 5 Inception blocks here, and then it goes to a max pool of same size as previous, then another Inception module, then goes the average, global average pooling. So, totally if we see here 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 Inception modules are kept in GoogleNet architecture, and after that one there is global average pooling, which is usually in other architectures we directly go to the fully connected layers. Here there is a global average pooling of size 7 cross 7 and stride 1. This reduces the parameters drastically and also prevents overfitting. And then it goes for a dropout, which once again it is a regularization technique in deep learning networks, and dropout is of 40%, and then we have the fully connected layers, then softmax and the output. So, this is the overall structure of GoogleNet architecture, and we will see GoogleNet architecture achieved a top 5 error rate of 6.67% in the ImageNet challenge in 2014 for the classification task, which is the winning result of that year. And it was a significant improvement over previous models like AlexNet, which was having 15.3% top 5 error, and VGG having 7.3% top 5 error. So, GoogleNet improved over the VGG family using the Inception modules. Now, GoogleNet has 22 layers, so during training the gradient of signal weakens as it moves backward. This is the vanishing gradient problem, which we have seen. Vanishing gradient problem, lot of times it comes into picture when the neural network is very deep, because if the gradient is small while it is coming towards the deeper portion of the architecture, it starts vanishing. To mitigate this problem, two small classifiers have been added to this model. What are these? These are called auxiliary classifiers. They help in propagating the gradient in the backward direction to the earlier layers, improving the training stability. So, we mitigate the problem of vanishing gradient using auxiliary classifiers. So, what are these auxiliary classifiers? Where are they put? One of them is placed after Inception module 4a, another one after 4d, and they branch out from the main network. So, they come as side network and they add to the architecture. So, we will have a quick look into how auxiliary classifier is used or during the training of GoogleNet, and how does it look like. So, it has average pooling of 5 cross 5 stride 3. Then it has 1 cross 1 convolution of 128 filters. Then there is fully connected layers of 1024 neurons, dropout of probability 0.7, and then fully connected layers 1000 neurons for ImageNet class. So, and then this is working with the softmax activation function. So, this is the structure of the auxiliary classifier which is used during the training of GoogleNet. So, what happens is these auxiliary classifiers, they are coming as a branch, side branch, and they are adding up to the structure, GoogleNet architecture, where they give the gradients from these structures itself. Some gradient comes and they help in mitigating the vanishing gradient problem in the GoogleNet architecture. Okay. So, with this GoogleNet's V1 Inception module, this achievement is a good achievement. After this, they went for other variants of GoogleNet, which are like Inception V2, where it included improvements such as batch normalization and shortcut connections, refined inception modules by replacing larger convolution with smaller, more efficient ones, and that helped to change the overall accuracy, reducing the training time. Then they had Inception V3 in 2015. This is a refinement over V2 by using dilated convolutions that expand the network's receptive field without sacrificing the resolution, and these are called as atroz convolutions. So there are multiple this kind of advancements they have done to the GoogleNet architecture to improve the performance of the architecture. So with this one I come to the conclusion of this session. So I will quickly summarize on what we have studied. Today we have studied the VGG family of architecture, and we have seen VGG16 and VGG19's architecture. The only difference is there are 3 more convolution layers in VGG19 compared to VGG16, and this has made the architecture deeper, but have not proved to be very having a very significant performance improvement. Okay, so VGG16 won the prize of the image net large scale visual recognition challenge in 2014, and the main idea of VGG16, which is different from AlexNet, is instead of using large filters they used small 3x3 filters and they stacked them in layers, and this was the core idea of VGG family. And then after VGG16 became the runner up during the ImageNet challenge. The winner that year was GoogleNet, and GoogleNet's performance was better than VGG. And the reason behind that one is GoogleNet have used Inception modules, where the core idea is to use 1x1 convolution to reduce the dimension before high or large filters are put through. Okay, so that core idea or that Inception module have brought improvement in the performance because it was reducing the dimensions. And after GoogleNet's success in 2014, it was the winner, whereas VGG16 was the runner-up, first runner-up in the 2014 challenge. And after that one, there were other variants also which started coming, like Inception V2 and V3, but the main idea remains the same. Okay. So with this one, I conclude today's session. I hope you all have got an idea of how the progression of the standard CNN models are coming, has happened over a period of time, and what is the implication of each and every core idea, their innovations in their architecture. So in the next session, we will look into ResNet model, which is once again another standard a CNN model, which is very much used in computer vision tasks. So we will look into the details of ResNet model in my next session. Till that time, please keep learning. Thank you all.